Hello again. We're continuing our discussion on limits and whether or not they exist. We're going to talk about a new rule that's called L'Hopital's rule. It's not necessarily new, it might just be new to you. So let's get started. So let's say I'm trying to find the limit of a function. It's a rational function that has some smaller function on the top and some other smaller function on the bottom. So it is a quotient and I want to find the limit of that. Well, let's say I try and do that and I get either 0 over 0 or infinity over infinity. Now we know that that's not hopeless. We just need to try and manipulate those functions so that they don't really change in value and they don't change in behavior. They're just things that I can more easily replace x with a number and get an actual value out of, hopefully. So here's some examples of where that would happen. Here's e to the x minus 1 over sine x. Now if I try and replace x with 0 everywhere, I'm going to get 0 on the top and 0 on the bottom, giving me with 0 over 0. And then if I have natural log of x on the top and 1 minus x on the bottom, and I look at that as x approaches 1, well, if I try and plug 1 in for x, I'm going to get 0 on the top and 0 on the bottom, again 0 over 0. If I have a function that's x squared minus 9 on the top and the tangent of x plus 3 on the bottom, if I try to replace x with negative 3, then I'm going to get 0 over 0 again. And if I have 1 over x on the top and I have the tangent of x plus pi all over 2, and as x approaches 0, this time I'm going to get infinity over infinity, which is not nice, but I need to do something. Now, if I think of all the strategies that I've tried before, none of these are going to work because these don't have really factorable expressions anywhere that can be useful. They don't have any square roots. They don't have any parentheses that I can expand or anything like that. So I need to find another tool to use. Okay, so here's where L'Hopital's rule comes in. L'Hopital's rule says that if I can find the limit of a rational function, different function, where the derivative of f of x is in the numerator, and the derivative of g of x is in the denominator, and that limit actually exists and is equal to a number, then what L'Hopital's rule says is that that limit is equal to the limit of the original function. So I'm not saying do the quotient rule. That's something totally different. What I'm doing is creating a whole new function that has the derivative of f on the top and the derivative of g on the bottom, and I'm seeing if that exists. And if it does, then that limit is equal to the limit of the original function. Okay, so let's be clear about that. All right, so let's look at the first example that I showed you, and there it is. So what I'm going to do is I'm going to look at f of x on the top. That's e to the x minus 1. Well, the derivative of that is going to be e to the x. And g of x, which is on the bottom, is sine of x. So if I take the derivative of that, I will get cosine of x. So instead of looking at the limit as x approaches 0 of e to the x minus 1 over sine x, I'm going to look at the limit as x approaches 0 of the derivatives of those, e to the x over cosine x. And I'm going to try and plug 0 into both of those. If I do, then what I get is 1. I get 1 over 1, which is 1. What that means, according to L'Hopital's rule, is the original limit is also equal to 1. Okay, it's kind of a cool little rule, and you can repeat it. If the first derivative doesn't work, you can use the second derivative and so on until something works. All right, here's the second example. I have natural log of x over 1 minus x, and remember that didn't work. That gave me 0 over 0. So the derivative of the natural log of x is going to be 1 over x, and the derivative of the bottom, 1 minus x, is just going to be negative 1. So my new function, my new limit is going to be the limit as x approaches 1 of 1 over x over negative 1. And if I try to replace x with 1 again, then I get negative 1. What that means is the limit of our original function is negative 1. All right, here's the third example. All right, f of x is x squared minus 9. So the derivative of that is going to be 2x. The bottom function is tan of x plus 3. And the derivative of that is the secant squared of x plus 3. So here's our new limit with the derivative of the top on top and the derivative of the bottom on bottom. Okay, if I replace x with negative 3 this time, it does exist and it's equal to negative 6. So that means the original limit is equal to negative 6. The last one is a little bit tricky because what's going to happen is If I try and take the derivative of the top, I get negative 1 over x squared, which still does me no good. And if I try and take the derivative of the bottom, I get negative 1/2 secant squared x plus pi over 2, and that doesn't help me either. Okay, so if I try and plug x equals 0 into that, I get a problem again, which is negative infinity over infinity. Again, that's not hopeless, but it's really not going to help. And if I do this multiple times, as I mentioned before, the derivatives are just going to get worse and worse and worse, and I'll still end up with negative infinity over infinity or positive infinity over infinity. So this strategy is not going to work with the function as it is. But I don't want to give up hope, so what I can do is I can rewrite the original function that I was given. It's kind of weird. It's got a fraction within a fraction. It's got a tangent. Maybe I can rewrite those as something. So the 1 over x in the numerator I can replace with just an x in the denominator. And the tangent of x plus pi over 2, I can split that into sine over cosine. And since it's in the denominator, the cosine will go on top and the sine will go on the bottom. And maybe that will give me a better result. So if I look at just the top, now my f of x is the cosine of x plus pi all over 2. The derivative of that is negative 1/2 times the sine of x plus pi all over 2, and that's by using the chain rule. Now if I look at g of x, I've got a product there, so I have to be careful. I have to use the product rule on that, and there's a little bit of chain in there too. So my derivative is going to be the sine of x plus pi over 2 plus 1/2 x times the cosine of x plus pi all over 2. So kind of tricky, but that is the derivative if you use the product rule and the chain rule. So there's my messy function right there. Messy to write down, but it is actually nice because now if I replace x with 0, that part of the denominator becomes 0, so I don't need to worry about that. And then I notice that the sine of x plus pi over 2 and top and bottom can divide out, so all I'm left with is negative 1/2. And what that means is the original limit is equal to negative 1/2. So those are our examples. There will be more in class tomorrow. If you have any questions, please let me know, and I will see you tomorrow.